Good morning, or good evening, or good afternoon to whatever time you're watching this lecture. In this lecture, we will be discussing the different basic inorganic principles. So, to begin, let's start with a very basic definition of the fundamental structure of matter, which is an atom. So, an atom is defined as the smallest unit that retains the property of an element, and the smallest unit into which matter can be divided without the release of electrically charged particles. So atoms make up our elements, and atoms cannot be broken down into other substances except if you're going to perform nuclear fission or nuclear fusion. Okay? So to recap our different classifications of matter based on our previous discussion, we have learned that a mixture contains substances, and substances are made out of elements, and elements are made out of atoms. Atoms are the smallest form of matter that gives an element its properties. However, atoms do have more fundamental particles. So what makes up atoms are the protons, electrons, and neutrons, which we will be discussing in a next slide. So the most famous definition has been published by Dalton in his atomic theory. All matter is composed of atoms, and this cannot be made or destroyed. All atoms of the same element have identical, and different elements have different types of atoms. Chemical reactions occur when atoms are rearranged. So that is our definition of an atom by our scientist Dalton. Now, atoms primarily consist of our fundamental particles. Particularly, we have our protons, which are positively charged. We have our electrons, which are electrically or negatively charged. And we have our neutrons, which have no charge. Okay? Protons, positive, electrons, negative. Neutrons have no charge. And when we usually describe an element, there is a standard notation to denote the atomic number, the atomic mass, and the element itself. So the standard method of symbolizing an element is to write elements. So this is our element. We write our mass number as a superscript, and we write our atomic number. We write our mass number as a superscript, and we write our atomic number as our subscript. So this is our mass number. So the atomic number is defined by the number of protons. Okay? So the atomic number of an element is defined by the number of protons of the element. Okay? And the atomic mass, or the mass number, is the sum of the number of protons and the number of neutrons. Okay? So please take note that the atomic number of elements do not change. The number of protons for each element stays the same no matter what isotope it is. Okay? Although the mass number is based on the sum of the neutrons and protons, it's not always the case that the same element will have the same mass number. It will always have the same atomic number, but it may not have the same atomic mass or mass number all the time. Okay? And this is where our isotopes come in. So within an element, the atomic number, that is the number of protons and electrons, are always the same. Atomic number of protons or electrons. This is, we are talking about an element. So an element is always neutral. So there is no charge. Since our atomic number is the number of protons and there is no charge, therefore there is the same number of electrons as well, since an element has no charge. Okay? An element will always have the same atomic number, but the number of neutrons can vary. If you have different numbers of neutrons, the mass number varies because our mass number, if you recall, equals protons plus neutrons. Since our protons are always the same and neutrons can vary, your mass number can also vary as well. Okay, so various elements with different mass numbers are possible versions of an element, and these are called isotopes. Isotopes are versions of an element which have different mass numbers. So take for example, let's have sample questions. How many neutrons are in each isotope of oxygen? Write the symbol of each isotope. So we have oxygen. We know that the atomic number of oxygen is 8. Okay? So oxygen will always have 8. We are now to compute for the mass number. So oxygen 16, it has a mass number of 16. Therefore, oxygen 16, oxygen 17, and oxygen 18. How many neutrons are there in oxygen 16? So 16 atomic, remember that mass number equals protons plus neutrons. Therefore, neutrons equals mass number minus proton. And remember, our protons are always the same. So every time that is 16 minus 8, 17 minus 8, and 18 minus 8. So the amount of neutrons is 8, 9, 10. Okay, so N here is 8, and here is 9, and N here is. Okay, so we have the same answer as the sample problem. Okay, recall that mass number varies while atomic number does not. So we have on the screen the isotopes of hydrogen. Since hydrogen usually is protium, deuterium, and tritium, protium only has one. Actually, it doesn't have any neutrons at all. It only has one proton. For our deuterium, it has one proton and one neutron. And for our tritium, it has two neutrons and one protons. Remember that the number of protons will never change. Since the atomic number of hydrogen is 1, the proton will always be 1, and the electrons will also be always. Isotopes of elements are identified by their mass numbers. Hence, isotope C14 is the form of carbon that contains 8 neutrons. The mass number gives the total number of protons and neutrons in an atom of an element, but it does not convey the absolute mass of an atom. Please do not confuse mass number with molecular mass or molar mass. We will be discussing molar mass in a future topic, particularly in stoichiometry. But for now, mass number is slightly irrelevant to the weight of an actual atom. For now, slightly irrelevant. Since we do not usually deal with one atom, we always deal with a group of atoms. So now that we know the parts of an atom, let's talk about the starting the starting models of different atomic structures. So since they knew that there are protons, there are neutrons, and there are electrons that make up an atom, they theorized different models in which it could best demonstrate what could an atom look like. So first, we have Thomson's Plum pudding model. So in the Plum pudding model, he proposed that an atom consists of negative electrons embedded in a positive pool, like raisins in a plum pudding. So it looks like a cookie, since plum pudding is usually not available in the Philippines. It looks like a chocolate chip cookies, in which electrons are the chocolate chips and the cookie itself is the positive pool. The next model is our Rutherford model. So the Rutherford model actually originated with our cathode ray tube experiments, which led to the discovery of the electron, the neutron, and the proton. They ran a slight variation of the cathode ray experiments, in which they shot the ray into a gold foil. So this is the gold foil experiment. The gold foil experiment suggested that an atom is mostly empty space with a tiny, dense, positively charged nucleus. The next model was devised by Niels Bohr, and in his model of atoms, Niels Bohr proposed that electrons can only circle the nucleus on fixed orbits in which the electron has a fixed angular momentum. Each of these orbits has a certain radius, or the distance from the nucleus, in which it has proportionality to its energy. This means the farther the electron is from the nucleus, the stronger its energy. So electrons can only change between fixed energy levels, which can be seen as light emission. So these fixed energy levels are defined as the principal quantum number, or n. We will be discussing quantum numbers in a moment. And this is the only quantum number introduced by the Bohr model of an atom. Please note that as the value of n increases, the electron is further away from the nucleus. The further away it is from the nucleus, the less tightly bound is the electron to the nucleus, and generally, the more it can react. The next model to be developed after our Bohr's model is the quantum mechanical model. So the Austrian Edwin Schrödinger formulated wave mechanics to explain the behavior of electrons in terms of wave properties. Werner Heisenberg from Germany developed an atomic theory using matrix mathematics, and Schrödinger and Heisenberg's work between 1925 and 1928 contributed to the formulation of quantum mechanics. In the quantum mechanical model of an atom, electrons surround the nucleus in orbitals, which are in regions called shells. So shells contain orbitals, and orbitals contain electrons. Okay? Shells could be thought of as a group of orbital. And the atomic orbital is a volume of space surrounding the nucleus where there is a certain probability of finding the electron. So electrons do not move randomly. There is a path they take, and there are chances where you can meet the electron or you may not meet the electron. So along with the quantum mechanical model came about the discovery or the invention of quantum numbers. So quantum numbers, or our wave numbers, can describe the position of an electron or where you can find it in our atom. The first quantum number is our principal quantum number. So this actually originated from our Bohr model. The principal quantum number tells which shell the electron is in and can take on integral values starting with 1. Remember that the higher the principal quantum number, the farther the orbital is from our nucleus. Okay? Our principal quantum number is usually in numbers 1, 2, 3, 4, 5, 6. However, there are letter counterparts K, L, M, N, O, P, which are in capitals to denote which shell the electron is in. So that is our principal quantum number. Next, we have our angular momentum quantum number. So this is symbolized by the letter L, but we usually write it as L, just for clarity's sake. So the angular momentum quantum numbers gives the shape of an orbital. Okay? It characterizes the shape of an orbital. We use numbers traditionally, but we can also use numbers to denote the shape of an orbital. What is common is we use numbers instead. So we have our S, we have our P, and we have D, and we have our F. S is usually a sphere. P is a dumbbell. D is a cloverleaf. And F is something hard to describe as a shape. You can judge for yourself once you see the shape of the F orbital. The next quantum number is the magnetic quantum number. So the magnetic quantum number, ML, gives the orientation of the orbital in space. The allowable values for ML are integer values ranging from 1, 0, and -1. So magnetic quantum number can also be written as M, not milliliters. Okay? And it can only range from -1, 0, and +1. Next is the spin quantum number. So the spin quantum number is symbolized by Ms. The spin quantum number tells us how the electron spins around its own axis. Its value can be +1/2 or -1/2, indicating a spin in either a clockwise or a counterclockwise direction. Next is our electron configuration. So this is the application of our quantum mechanical model. So the electron configuration is the distribution of electrons of an atom or molecule in an atomic or molecular orbital. The format of an electron configuration is usually the most basic one is you write a number Write the letter, and you have a superscript on the letter denoting the number of electrons for that particular configuration. Okay, so the number represents the principal quantum number. The letter could be S, P, D, or F. This represents the shape of the orbital. And the superscript denotes how many electrons are on the orbital. Okay, so this is the general structure of an electron configuration. Usually you won't find one alone. It will be a long chain of this repeating pattern here. And to understand it better, let's discuss how to get an electron configuration. But before we move there, let us first discuss the rules in electron configuration. Okay, so first we have our Aufbau's principle. This principle dictates that the lowest energy orbital fills up first according to the order 1s1, 2s2, 2p, 3s, 3p, 4s, 3d. So there is a pattern to this which I will be posting later. And you have to follow this order. You cannot go from 1s to 2p. You must first pass 2s, then 2p. You cannot skip any. You have to fill the orbitals in order, because otherwise you won't form a stable element. Next is your Pauli's exclusion principle. So this states that the spin has only two possible orientation, up and down. And only two electrons can occupy an orbital, and they must be of opposite spin. Okay? So this is important. Only two electrons can occupy an orbital. It is not possible for three to occupy. Four, not possible. Zero, yes, there could be a presence of an empty orbital. You can also have a half-filled orbital which only has one electron, but never three, never four. And they must be of opposite spin. And finally, you have Hund's rule. If two or more empty orbitals of equal energy are available, only one electron occupies each with the spins parallel until orbitals are half full. So I will demonstrate later how to perform Hund's rule. So let's take the rules, or how do we get an electron configuration of a substance. So before you write the electron configuration, you should know the number of electrons for that substance. Remember, for elements electrons are equal to the number of protons, and it is also equal to its atomic number. Please take note, this is only applicable for elements. Since ions tend to lose and gain electrons, this is not applicable for them. The order in which electrons are placed into the orbitals is based on the order of their energy. This is called our Aufbau principle. This means that lowest energy orbitals will fill first, and these are obtained by calculation. So the main reason why we have this pattern is because it was proven by calculation. So this is the order of fill. So you have 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so on. There is a pattern for this. So you could use a mnemonic to memorize the electron configuration pattern for our Aufbau principle. Now remember that each sublevel can only accommodate a certain number of orbitals. This is what our sublevel is. Our sublevel is also the shape of our electron. And each sublevel can only contain a certain number of orbitals. So S can only have 1 orbital, P only has 3 orbitals, D has 5, and F has 7. Please do recall that each orbital can accommodate 2 electrons. Hence, totally filled orbitals can accommodate S can have 2, P can have 6, D can have 10, F can have 14 electrons. Okay, so let's try it out. So first we have our hydrogen element. Okay, so hydrogen basically has 1 electron. So what is the first orbital to be filled? It is 1s. You will always start with 1s. So 1s. How many electrons do you have? 1. 1s, 1. Very easy. And if you are going to represent that in boxes, S has how many orbitals? It can only accommodate 1 orbital. You represent each orbital as a box. And you're going to represent each electron as a arrow. Okay? Remember of our Pauli's exclusion principle, each orbital can only accommodate up to 2. And for our Hund's rule, you have to fill each orbital in order with parallel spins. Since we only have 1 electron, you will only need 1 electron for our hydrogen. Very easy. Since you only have 1 electron. Let's take a sample at the next element. Let's have carbon. Carbon 6 has 6 electrons. So we will start with 1s. 1 or 1s2. You're going to start with 1s2 since an orbital can fill up to 2 electrons. Up, down. 2 electrons. How many electrons are left? There are 4 electrons left. So you still have 4 electrons. What is the next to 1s1? 1s? 2s. 2s, 2. It is also completely filled. And finally, you have your P. 2, P. But in this case, how many electrons are left? You have 2, 2 here, 2 here. So you only need 2 more electrons for you to have 6. Okay? 2p, p can accommodate 3 orbitals. Okay. Now if I write it this way, this is wrong. 2p, 2. This is wrong. Since, according to our Hund's rule, you have to fill each orbital first in parallel spins. So this is wrong. Don't copy this. You have to put it this way. Okay. Please take note that the outermost shell is your valence shell. So your valence shell is 2. And the electrons on the valence shell are called your valence electrons. Okay, this will have a greater purpose later in bonding, and in our reactivity. So for our carbon, it has 4 valence electrons. Next, let's bring out an example. Sodium element. So it has 11. So let's start. 1s2, 2s2, 2p6. Can also fill because 2 plus 2 is 4 plus 6, 10. Finally is 3s. 1. 2 plus 2, 10 plus 6. 2 plus 2, 4 plus 6, 10 plus 1 equals 11. I'm not gonna draw it anymore. Let's just draw the final shell. Okay, so sodium has 1 valence electron. Next, let's have chloride element. Sorry, it was chlorine element, not chloride. So our chlorine element has 17 electrons. Let's fill it up. 1s2, 2, 2s2, 4, 2p6, 10, 3s2, 12, and 3p4. 5, sorry. 10, 12, 15, 17, sorry, 17. Okay, so we have 17 electrons. I'm not gonna fill it up completely. I'm just gonna fill the last shell. Okay, so 3p5, how many orbitals can p accommodate? It can accommodate up to 3. Okay, and based on our Hund's rule, you are to write them down in parallel first. And we have 2 left. So 1, 2, 3, 4, 5. This is our chlorine element. Let's draw S as well. And this is the valence shell of our chlorine. Chlorine has 7 valence electrons. Next element is gold. So gold has 79 electrons. So it has a bit longer electron configuration. And it will now take into account different shells and higher shells and higher letters. Okay, so let's start with 1s2, 2s2, 2p6. So this is already 10. 3s2, 3p6, 3d10. Okay, continue. 4s2, 4p6, 4d10, 5s2. So how many is it already? Baka tayo lumabas. This one is 10. 28. This one is 48 already. Okay. From 5s2, we have 5p6, 4f14, 5d10, and finally we have 6s. Check how many s? 48. 48 plus 6 is 54. 54 plus 14 is 68. 68 plus 10 is 78. And finally, S1. 79 electrons. Okay, so as long as you memorize our as long as you memorize our fills or the pattern of how to fill our electron configuration, you could have easier uh, you will have an easier time filling up our electron configuration. So I will leave the next element for your practice, which is our astatine. Please solve at your own time.